Hi, my name is Paul from Physics High, and today I'm going to do another series of questions for Module 6, in other words, dealing with electromagnetism, and today I'm going to look exclusively at the 2010 HSC paper. If you don't do the HSC in New South Wales, these questions are still relevant. I'm basically dealing with charges and fields, motor effect, and electromagnetic induction, and also the related applications. So this may be useful. Now, like all these videos, it's worthwhile to actually attempt the questions before you continue. So either look at the link in the description below on my website. You can download a copy of the questions to do yourself beforehand, or you could just simply pause the video and have an attempt at the question. And remember, I really value your support. Click the link down below, buy me a coffee, and to help support the work that I do. So let's get started. Our first question is a multiple choice question, and it says, while drilling into a tough material, the DC motor in an electric drill is slowed significantly, and what this causes its coils to overheat. And why do these coils overheat? Well, a DC motor in essence is a spinning coil in a magnetic field. As it turns, there is an automatic back EMF that lowers the effective voltage. So in essence, if I simplify this, let's say we have a very simplified loop of wire in a magnetic field, and we'll make this our positive and this at our negative, and of course there's a north on this side and a south on this side. As this starts to turn, in this case we're going to have it turning in a counterclockwise direction because the current is going into that direction. The EMF is in that direction, but as it turns, it's experiencing a rate of change of flux. As a result, it's getting a back EMF. So the effective voltage is decreased. So you might apply 12 volts to it, but the effective voltage is maybe 8 volts, for example, and so the effective current actually, as a result, is decreased. Now, there is a system in play to adjust for that when you first turn the rotor on. So when the drill suddenly stops, what goes on? Well, suddenly as it stops, we no longer have the back EMF, and suddenly we have a huge spike in the effective EMF, which means a huge spike in current, which can affect also burn out the motor. So with those options, let's have a look at why the coils overheat. Well, A, the resistance of the coils increases significantly. Actually, no, the resistance of the coils don't change. They're still the same. So A is incorrect. Increased friction in the drill converted to heat? No, it's not about that either. C, the back EMF decreases. We've just discussed that. And so the current in the coil increases. That's exactly what's happened. Let's just double check with D. The induced eddy currents increase, and so more heat is produced. That's not the case here because we're not inducing eddy currents. We're actually taking away any so-called electromagnetic induction. So that is incorrect. So there is the answer for question number 8. Question number 9, a high voltage is used to transmit electrical energy from power stations to users. Now, it says, why is it high voltage? Well, in essence, it's the ability to transform it. So here is my power station, very beautifully drawn. And of course, that's going to be transmitted eventually to your house on this side. You want to reduce the energy loss along the way. In other words, the energy loss, or the power loss more specifically, is simply equal to or proportional to I squared R. So if you have a step up transformer over here that steps up the voltage, that means you have a reduction in current automatically, which means you have a reduction in the power loss because it's a square relationship. And over here, you'll have a step down transformer, which means your voltage will get dropped down to normal. You get an increase in current, but of course that's what supplies your home. So looking at our responses, it helps protect the system from lightning strikes. No, that's not the case. It allows supporting structures to have smaller insulators. Again, that's not the case. C, it minimizes the effects of electrical resistance of the wires. Well, this is exactly what we're talking about. It has a certain resistance, but of course we don't want heat loss due to resistance. So C is the correct answer. What about D? It ensures that even with voltage losses, 240 volts will still reach the user. It's actual about conversion, and it's about energy loss. So therefore, this is not the answer. Question number 10. The diagram shows a model of a transformer in a circuit. Which of the following correctly identifies part 1 and part 2 and the function of this transformer? Okay, so what we have is here is our supply. So here's our source, and you'll see you have a number of loops over here. So this over here is our primary coil here, and so therefore this is our voltage primary. Therefore electromagnetic induction takes place, but we'll have a change in the voltage. My secondary coil is on this side. We have an increase the number of turns of wires. So as a result, this is a step up transformer because we're increasing the number of turns in the wire. That will result in a circuit being closed here that you'll have a current as well. Now, what's 1 and what's 2? Well, we got 2 is our primary coil. Our 1 is our secondary coil. So let's have a look at this. Our primary coil is going to be in 2. So there's primary right there. So that's correct. And that's correct over here. Number 1 is our secondary coil. So that's correct. And that's correct. Oh, so far we're happy what we're going. But of course what's happening is the voltage is stepped up. We've already established that. So it's stepped up here and stepped up there. So therefore D is our answer. Question number 11. 2 copper rings lie in the same plane as shown. An increasing current flows clockwise around the outer ring. What happens to the inner ring? Okay, so what we have, if we have an increasing current over here, we have an increasing change of flux, but because of Lenz's law, that any action opposes that one that generates it, that means that if you have an increasing current in the inner core, you're going to also have an increase in current in the secondary coil, or it's over here. But is that the current may increase, but its direction won't be. The direction will be in the opposite direction because it has to therefore be consistent with Lenz's law, which is all about conservation of energy. And so as a result, the current in this case is going to go in the counterclockwise direction. So what happens? It's an increasing current, but it's anti-clockwise. So D is our answer. Question number 15, we have a charged particle Q. It enters a uniform magnetic field at a velocity. The particle follows a circular path with radius r. If the magnitude of the magnetic field were doubled and all other variables were kept constant, what will the new radius be? Well, what's the principle here? The principle here is that the charge is experiencing centripetal force. So we have mv squared over r is our centripetal force. But what's causing it? Well, it's the Lorentz force, which is QVB. Now we're going to look at changing our magnetic field and see how that affects the radius. So what we're going to do is we're going to rearrange that formula. So what we end up doing, our V's cancel out to, and therefore our B, our magnetic field, will simply be equal to mv over QR. Now we're told everything else is kept the same. So what's happening here? We are told that M is kept the same, V is kept the same, Q is kept the same. All we're doing is changing the magnetic field. Well, if R gets bigger here, then B gets smaller. So if R gets smaller, it's because B gets bigger. You can see it's an inverse relationship, which means that as B gets bigger, R has to therefore decrease by the same number. So therefore B is our answer. Question number 16. A cathode ray beam strikes a screen at point P, producing a bright spot. The north end of the magnet is brought towards the beam, and then we're asked, which way does the spot move? All right, there's a couple of things going on here. It's a beam, a cathode beam, so we know these are electrons coming out. So I want you to do this yourself. What we have, first of all, is electrons coming towards us from your perspective. But remembering electrons are negatively charged, so we know straight away that what we have is we have a conventional current in the opposite direction. So we all agree the conventional current is now going into the page. The next thing we're told is we have a magnetic field. Now those magnetic fields are running across the page like this. So automatically we know we're going to get a force because our current and our magnetic field are perpendicular to each other. The point is, which direction is the force? Well, here comes your palm rule. We use the right-hand palm rule. For this case, it's like the motor effect. In this case, I'm going to have my fingers going across the page. Remember, conventional current says it's going that way. Therefore, the beam will get pushed up, and so therefore the answer is going to be A. Now, if some of you know the Fleming's rule, this is the rule that you're going to be using, and the way to remember it is FBI. And so again, we do the same thing. What is I? Well, I is going to go into the page because it's conventional current. Magnetic field is going across, so it's this way. You'll see my force is going upwards. Again, it's consistent. A is our answer. This question here is a more challenging question, and considering this is the last question in the multiple choice section, it's meant to be a bit more challenging, but you need to carefully see what's going on. We have a DC motor, but the circuit is designed in such a way that the current is not applied to the coil, it's also set up to give you the magnets that actually allow for the coil to experience a force. So we need to carefully see in which circuit will the rotor turn in a clockwise direction. Now we know this is positive, and if you follow this along, this goes up like this and forms a coil that is going from our perspective around that way. Now, how do we establish which end is the north? Well, if my current is going to go in that direction, I curl my hands across in that direction, and that automatically means my north is at that end. But that means I've got my south on this end. So automatically I know that this here is a south. If you look at this diagram, this is the same diagram, so this is also going to be the south on this side. Over here, this again is the same diagram. This goes up and goes around and goes this way, so this is the south. All of these have the south on this side. Let's have a look at the other side. Now, if we follow the current along, then the current is going to go in that way, and again it's going to go over the top and back out again. So we've still got that same idea on that one over here, and so as a result my north is actually on this side, which is the side we want, and so far that's excellent. On the other side, you see it's also negative. We've got the same design. We have the north on this side, but here things are starting to look different. So what we have is that the current is going this way, but now it's going in the opposite direction. And being in the opposite direction, it's putting my north in this side and therefore the south on the inside. And so therefore I'm going to have a south here and a south here. Automatically you'll see that in these four options, two get discounted because you can't have two souths, and we need a magnetic field that runs from left to right or right to left, and so therefore we can discount these two options. So now let's have a look what's happening in the coils here. We have a current in this case coming here, and it's going in that direction and that direction for this guy, and in this case we have the current going in that direction and that direction for that guy. But now automatically we have enough information to work out which way each is going to turn. Now looking at part A, and I'm just looking at the north aspect over here, so this is the one I'm looking over here. I have my magnetic field going this direction. I have my current going in that direction, and that means I'm going to get a force that is in that direction. That automatically tells me this is going to go in a counterclockwise or anti-clockwise direction. Well, this is going to go, in this case, downward here, and therefore this is my correct answer. Moving away from multiple choice questions, now we're looking at a short answer response, and in this case it's actually a graphical type of situation. So in other words, this is a question that is particularly targeting those students that are in bands 4, 5 and 6. So let's examine this question and let's break it apart. There are two parts to this question. A magnet is dropped through a center of a solenoid connected to a data logger, and of course we've got the voltage going on, and it says y is the magnitude of the potential difference at y greater than at x, and the magnitude is again dropped with two changes being made. It's dropped from a greater height, and the south pole of the magnet is pointing downwards, and we have to sketch a graph and compare that to our original graph. Now what is going on here? This is all about electromagnetic induction and also Lenz's law. So we've got a magnet dropping down, which, because of the fact that the coil is experiencing a changing flux, a rate of change of flux, and as a result an EMF is being generated. So as it falls, you can see that the voltage increases at the point of X. Now once it travels through the tube, it's traveling at a constant velocity, but now its velocity starts to increase as it stops getting towards the other end. It's now moving faster at the bottom than it was at the top. So since it was moving faster, the rate of change of flux is actually greater. But of course it's in the opposite end, so therefore the voltage is going to be a negative value. So I've just answered part A. The potential difference at Y is greater because the rate of change of flux is greater because it's moving faster. That addresses part A. But let's have a look at now, how would we change this if we were to drop it from a greater height? A couple of things you need to consider. First of all, we're going to change the pole so it goes the other direction. So the first thing you should notice is that the polarity is going to be in the opposite direction. In other words, instead of having a positive peak and a negative peak, our new graph should have a negative peak and a positive peak. So that's the first change. The second change is that it's going to be dropped from a greater height. That means the velocity at which it enters the pipe is actually going to be faster than the original setup. So we're going to have automatically a higher voltage to begin with. So here we've got a value of around 0.5. It's going to be higher than that. And of course the secondary peak will also be of a greater amplitude, but of course again in the opposite direction. But there are two other key things to change. Since we are dropping it from a greater height, it's going to take a little longer to actually go through. And secondly, the velocity at which it enters is higher, therefore the velocity inside the tube will be therefore much higher, therefore will take shorter amount of time to pass through the whole loop. So in order to really appreciate all of the things I've just mentioned, I'm going to draw the graph on the graph that we've provided so that you can clearly see the difference. It's going to arrive later, so I'm going to start over here. It's going to have a larger peak like so, and of course it's going to return with a much higher peak like this, and you'll notice that the way I've drawn it is that the time that is occurring, which is the time from here to the time from here, is shorter than the time from here to here. So it arrives later, but the time for it to pass through is much, much shorter. And of course the peaks are taller, with the secondary peak being taller than our first peak. And therefore that's worth 3 marks. What we're looking for is a shorter difference between the whole path. We're looking at a flipping of the polarity, and we're looking at higher peaks because of the greater rate of change of flux. Question 28. Now in this case we're dealing with basically a bar or a current that's passing through a wire, and it's going to experience a force on our electric balance. And this question is quite involved, so you need to take this very carefully, because what's happening here is our electric balance here is always going to be reading a value in kilograms when it's actually responding to the concept of force or its weight. So let's read it. A copper rod is placed on a wooden frame, it's placed on an electronic balance, and a length of 0.2 meters of the rod passes at right angles to the horizontal magnetic field, which is what we've got here. A current of 0.3 amps is passed along the rod. The reading of the balance increases by this amount. What is the strength and direction of the magnetic field? First of all, we have a motor effect going on here. Since the mass or the mass reading increases, what's happening? Well, it's experiencing a force in the downward direction. Since my current is going across that direction, using my hand rule, it establishes that the magnetic field, of course the force being downward, being the current being that direction, the magnetic field is into the page, and the way that we draw that is by a series of crosses like so. So therefore we understand that the magnetic field is going into the page. So we've addressed part of the question, and we now need to work out, well, what is the strength of the magnetic field? Our magnetic field is resulting in a force. So we have F is equal to BIL. We're interested in B, of course, so B becomes F over IL. Now what is our force? The mass increases by that amount. So the force is 7.5 by 10 to the power of -4, but of course it's multiplied by the acceleration due to gravity, which is 9.8. We divide this by I and L. our I is 0.3 amps and our L is going to be only 0.2 meters. And so therefore a magnetic field can be determined, and simply that's just a calculator problem now, and we're going to get 0.111225 Tesla. So there's the strength. We've already established the direction. Question's done. Now, why is it worth 4 marks? Because it's hoping that you have at least identified the correct mathematical equation, that you've identified the correct direction, and generally speaking, where most students fall down is they provide an answer there and forget to mention the direction of the magnetic field. And that ends our discussion on electromagnetism questions as they relate to the exam from 2010. Please like, share and subscribe. Put a comment down below if this has been helpful for you. And please remember, buy me a coffee if you want to support the work that I do. My name is Paul from Physics High. Take care and bye for now.